So why have the government programs failed? Well, they have too much money being spent on too few solutions. For instance, there are far too many tokamak designs. Another problem is the university lab settings. Now, in the university lab settings, the emphasis is not so much on making rapid progress as it is on understanding the science and also producing scientific papers, and of course, teaching the students how to do research. Now, I'm not saying that university lab settings are bad. I think we very much need them because we need to understand the science and we need to produce future scientists and engineers that know about fusion. But the problem is that it does lend itself to rather methodical type of research, and the progress is very slow. There's also a tendency to avoid risk, because if you try a new idea and it happens to fail, then your whole project might be canceled. Okay, so fortunately, it's not just the government research anymore. Some entrepreneurs have looked at this and decided that there must be a better way. I've listed here 6 companies that are now working on developing a fusion device. So why might private companies succeed where the government has failed? Well, one thing, they spend less time on theory and writing scientific papers. They're much more practical. They iterate more rapidly. They explore various options while spending as little money as possible on each option. And they do not fear failure. And also, they create breakthrough results. Now, history has shown that on very tough problems, it's often the private companies that succeed where the government has failed. So in the rest of this talk, I'm going to talk about one specific private company, and that's LPP Fusion. LPP Fusion was formerly called Lawrenceville Plasma Physics. And there have been a couple of talks at previous Mars Society conventions about this company. So it's possible that some of you may have already heard a talk about this company. Now, in the interest of full disclosure, I am an investor in this company. So and I think they're also very far ahead of the other 5 private companies that are listed here. So they use a completely different approach to fusion called the dense plasma focus. And there are 2 electrodes. The cylindrical one in the center there is the anode, and that's surrounded by those bars, which is the cathode electrode. They use, or will use, hydrogen and boron-11 fuel. And that's different than the fuel used by most fusion devices. But it has some advantages. One thing that is very plentiful on the Earth, it's very inexpensive, and you have essentially an unlimited supply. When you react those 2 fuels together, it's aneutronic, which means that it doesn't produce any neutrons. And because the fuels themselves are not radioactive and no neutrons are produced, you have no radioactive waste, absolutely 0 radioactive waste, which is a big advantage over some other fusion fuels that do produce some radioactive waste. And the fuels are completely safe, that there's no chance of a meltdown or any other kind of serious accident. Now this device exploits exploits fusion instabilities rather than trying to fight to overcome the instabilities as most of the other fusion devices do. It's very small. It's smaller than it appears in that picture, actually. You could easily hold either of the electrodes in one hand. It's inexpensive and can be mass-produced. And unfortunately, I tried the movie before, but it wasn't working on this computer. So I'll just describe what the device does. There's a sudden and very intense pulse of electricity which is discharged across the electrodes. And that pulse of electricity flows through the gas, which contains hydrogen boron 11. And as it travels through the electrodes, along the length of the electrode, these filaments form. And then those filaments merge into one filament, which goes through the center electrode. And then the instabilities cause that filament to kink and twist, and it produces this tiny plasmoid, which is only a few millimeters across. And so that plasmoid then creates the fusion, and you get this beam of charged particles, which emanates from the plasmoid. And then you have 200 of these electrical pulses every second. So that's what keeps the process going. Now, the way that electricity has been produced ever since the time of Thomas Edison is that you would burn the fuel. Burning the fuel produces heat. The heat produces steam. The steam turns a very large turbine, such as the one shown here. And the turbine turns a generator. Well, you can imagine that's a very expensive process because the machinery is very large and expensive, and there's a lot of maintenance. Well, with the focused fusion, we can do away with all that. And we can do what they call direct energy conversion. And the way that works is the focused fusion device creates a beam of moving charged particles. And moving charged particles are electricity. So you can simply capture the electricity with this high-tech transformer device and then feed the electricity to the grid. So because of this, the focused fusion device may be as much as 1/10 the cost of any existing energy source, as is shown in this chart. This is LPP Fusion's first experimental device, and they call it the FF1 for Focused Fusion 1. And the goal is to achieve break-even by the end of next year. Now, by break-even, we mean that you get more energy out of the device from the fusion than is input to the device. No fusion device thus far has achieved break-even. So if they achieve that goal, then they'll be ahead of everybody else. And their next goal is to create a commercial generator, one that actually contributes to the grid. And that one, they're hoping to do that 4 years after they succeed in achieving break-even, which if they succeed next year, then it would be the year 2021. Now, these are very, very ambitious goals. And they're going to need a lot of luck to achieve those goals, but it is possible. It may just take them more time, but it's certainly possible. There's no theoretical reason why this approach won't work. So that's their commercial fusion generator. it will produce 5 megawatts of power. Now that's enough to power about 4,000 homes. And it's also enough to power, say, an initial settlement on the moon or on Mars. This is very easily mass-produced, it's inexpensive, and it fits in a truck. In fact, with a very large truck, you might be able to fit more than one of these devices. Now, that's good because, say, if there was some natural disaster and a power plant was knocked out somewhere, you could just drive up with some of these devices and get the power up and running again very quickly. And it's small enough that it could fit in rockets of the size that exist today. So it can be used for propulsion. And I'll talk more about that later. So there are 3 conditions needed for break-even. They need to achieve a temperature of over 1.8 billion degrees. Now that is really, really hot. It's 200 times hotter than the center of the sun. Now, amazingly, LPP Fusion has already achieved that temperature in their FF1 device. So that's a major accomplishment that they made. The second requirement is that you have to maintain that temperature for a certain amount of time, called the confinement time, and in order to get net energy. And it's a very short amount of time, 8 nanoseconds. Well, the LPP Fusion has also achieved that goal. In fact, they've achieved a confinement time of 20 nanoseconds, which is 2.5 times what is needed. So they've done very well there also. Now, the third requirement is the one where they haven't met yet. And unfortunately, they still need to increase the density by a factor of 10,000 before they actually reach break even. So that's pending. But they think they know how to do that, and they think they can achieve that by the end of next year. So time will tell. So how do they stand in the race to produce fusion? Well, this is the triple product. If you remember the last slide I just showed, there are 3 requirements for fusion. And if you multiply those 3 things together, the density times the confinement time times the temperature, you get this, what we call triple product. It's a figure of merit that tells you more or less how well the device is working. Well, the Focus Fusion device is now in 5th place. Along the horizontal axis just shows the ranking. Now, that's not too bad, considering that the 4 devices that are ahead of it are all government devices. And those government devices all cost at least 100 times as much to develop. In 6th, 7th, and 8th place are some of the other private companies. So LPP Fusion with the FF-1 device is well ahead of the other private companies on this score. Now, another measure of how well you're doing is what we call the deuterium yield per unit energy input. And that's also known as the wall plug efficiency. And on that measure, Focus Fusion is in 2nd place. There's one government project ahead of it in 1st place, and there in 3rd and 4th place are 2 other government projects. And the other private efforts are, they fall below. They're well behind, so they don't show up on this chart. And I got just one more chart to show you. This is the same measure as the last plot, the wall plug efficiency, except they've divided that by the number of dollars spent on the project. So in other words, it sort of gives how much bang for the buck you're getting. And on that score, LPP Fusion is in first place because they've spent, total since the company was formed, they've spent about $5 million, which is all they've spent. All the other, they're in second, third, and fourth place are government projects, and those have spent, on the average, very roughly 100 times as much money. So policy change is needed. Almost no government funding has ever gone to any of these private companies. And the private companies are starved for lack of funds, and they could certainly make a lot quicker progress if they had more money. Now, I'm not saying you have to give them a lot of money because they spend money a lot more efficiently than the government does. So, I'm just saying what I'd like to see is increasing the fusion budget by maybe 5 or 10%, and then that extra 5 or 10% going to the private companies. So the Department of Energy should foster a competition. The competition might be something similar to what NASA has done with the commercial cargo and commercial crew, where they had a competition to deliver cargo and crew to the International Space Station. And also, they should fund several different companies. I'd like to see LPP Fusion succeed, of course, but you never can tell at this stage of the game which company might be the one to make the key breakthrough. So you have to look at several different companies. So next I'll talk about space propulsion. And the key parameter, if you're looking at rocket engine efficiency, is specific impulse. Chemical rockets have a specific impulse of 450 seconds. Nuclear thermal, about double that, 900 seconds. And today's state-of-the-art electric propulsion, those are ion engines, about 4,200 seconds. Well, the focused fusion device would have a specific impulse of about 1 million seconds. Now, that's orders of magnitude better than anything we have existing today. And I can't emphasize how much this would be a step change in capability over what we have today. It would be like going from the sailing ships at the time of Christopher Columbus to, the modern ocean liners that we have now. So what missions might be empowered if we got this focused fusion device working? Well, we could have human travel from Earth to Mars in only 2 weeks. We could have human exploration of the outer planet moons, Jupiter, Saturn, and beyond. We could have a reusable single stage to orbit, to Earth orbit that is, vehicle, which still carries a very large payload. And theoretically, with a multi-stage fusion rocket, we could travel at 1/3 of the speed of light. Now, that's not as good as warp drive, of course, but it's at the point where we're beginning to consider interstellar travel, especially for robotic probes. So, in conclusion, we really need fusion, both to solve the world's energy needs and to produce a big advance in space propulsion. And private industry may lead the way to the first successful fusion device. But a policy change is essential for this to happen. Fusion is hard, to be sure. It's a very difficult technology. But It belongs to that category of human achievement, such as the invention of the airplane, or reusable rockets, or humans landing on the moon, or humans landing on Mars. These things all seem impossible, but only up until the time that somebody does it. Okay, thank you. I'll have a couple of questions.
Could you explain how these extreme temperatures are achieved, how they're contained? I just don't understand any of the physics of this.
Right. Well, first you have to form the filaments, which the way they form, and it happens in nature also. If you look at the aurora borealis, for instance, you often see these filaments. It's a current running through a magnetic field, and whenever a current runs through a magnetic field, it has a pinch effect, so it tends to condense things into filaments. Now, these filaments will all merge into a single filament, and then what really gets the density to increase is that there are instabilities which cause that filament to kink and twist and actually form this very small plasmoid. And that's what does it. It sounds hard to believe, but they've actually measured that temperature.
I teach physics, and I don't understand a word of what you just said.
Okay, right. Over here?
Do you see much potential for lunar helium-3 in a fusion-based future?
Helium-3, yeah, that would be a good fuel too. Now, helium-3 isn't plentiful on the Earth. In fact, there's hardly any of it on the Earth. There is a lot on the moon. So some people, like Harrison Smith, who's an Apollo astronaut, advocates mining helium-3 on the moon. But of course, if you mine helium-3 on the moon, that's going to push up the cost. So would it be economical? I don't know. But that would also be a potential good fuel. Over here?
Me?
Yeah, sure.
I guess, well, two. How similar is this to Sandia National Labs Z-Pinch, their Z machine? And also, you make it seem like this could be used as a launch vehicle, or would this be used like an ion engine that has high ISP but low thrust?
Okay, I'm not familiar with the Z-Pinch machine, so
Okay.
I can't talk about that. I didn't go into all the propulsion stuff because it gets pretty complicated. But the 10,000 seconds of our 1 million seconds specific impulse, that's when it's used as an ion thruster. You essentially have these these helium nuclei which get expelled at extreme speeds. Now that will be low thrust, but there are also ways of getting high thrust out of this machine. It's just that the specific impulse will go down some when you go to the higher thrust. But you could hook it up to like a Vassimer rocket, which is something that is power hungry, wants a lot of electricity, and that would give you high thrust. But launching from the Earth would be even a different method, and I better not go into that because there are other questions here. Yeah, over here.
I have two questions. So one, these are really high temperatures. I'm just wondering about
Yes.
internal degradation of your system during operation, and if you have to keep replacing things. And my second question is, it's a very lofty goal. Fusion is always 50 years away,
Right.
whatever it is. So I guess why are you so confident, specifically in your design? Because it still needs a much higher density.
Well, for sure that there are huge challenges. Now, you mentioned the degradation of the materials. Specifically, the electrodes are the ones that are close to that ball of plasma, and whether they can withstand those temperatures when you're pulsing at 200 pulses per second, I'm not sure that we know that for sure yet. So it's not you know, this is a risky, you know, you wouldn't want to invest unless, you know, you had enough money that you wouldn't want to put your life savings into this. So it is risky. What was the other part of your question?
No, it was just thermal degradation, and also like it's a very difficult goal because no one's ever done it. You still need a great increase in density.
It is difficult, but if you look at the history of of achieving hard things, like the invention of the airplane, the U.S. government funded Samuel Langley to invent an aircraft, and he failed. And then the Wright brothers came along, and they didn't have any government funding. They succeeded. And, there are a lot of other examples like that also. It's hard, but, things like landing humans on Mars are hard, but I think that's going to happen too. Eventually, somebody will figure out how to make that work. There are dozens of fusion devices that might work, it's just find the right one.
What is the current output for the plasma fluid?
The current?
The current. What is the current?
Oh, the current. Well, I don't know right now what the current is. I'm not the scientist, but they have 8 capacitors which they're using at present. They have 12 capacitors, so they could use the other 4.
What are the capacitors?
That I'm not sure. But they also think that the density is going to go up exponentially as you increase the current. So that's one of the ways that they think they can reach break-even. As they increase the current, your density will go up exponentially, and hopefully it will work then. Yeah, over here.
This is like sonoluminescence, correct? You have very small pockets of extreme high density and heat.
Yes.
But the entire device is not operating at that temperature.
Yes.
So you have very small areas that would produce enough energy to create fusion, but you're not putting that entire chamber at that pressure and heat.
That's exactly right. Your tiny ball of plasma is only a few millimeters across. That's never going to come in contact with the electrodes.
That's your actual reactor, is that tiny little plasmoid, right?
That tiny little plasmoid is what produces the heat. And that doesn't come in contact with the electrodes. Electrodes will be cooled with some kind of cooling flow, like you cool turbine blades. Now, whether that will be enough, I don't know, but time will tell. Maybe one more question, because is the next speaker here yet?
No, actually, the next talk is cancelled, so we have time to approve. So
You're stuck.
I want to continue.
Oh, okay.
You gotta stay another 30 minutes.
Oh, okay.
No overtime.
Right here, then.
What happens to the boron 11? Is it catalyst or fuel?
Yeah, it's one of the 2 fuels. The hydrogen nucleus, which is really just a proton, merges with the boron 11, and for an instant it forms a carbon molecule, carbon 12. But the carbon molecule is unstable, so it quickly breaks up into 3 helium nucleuses.
And that's what you harvest, the helium nuclei, the alpha radiation is what you harvest to produce the electricity?
Yeah,
Scraps of metal?
right. As it fuses and then breaks apart, it produces the electricity. But yeah, that's right. Let me take another question. How do they get the electricity out? It's that high-tech transformer device, which the focused fusion device produces this beam of moving charged particles, and moving charged particles are electricity. And the beam goes through these coils, and it's like a transformer. So it conditions the beam so that the electricity can be added to the grid. It's really, yeah, that's right. It's really a very simple That part of it is easy, I think. And what's hard is, actually getting the fusion.
And you said you only spent $5 million.
That's
Where's your
total.
company located and
Well, I'm,
what's the next round of funding?
okay. I'm an investor. I'm not from the company. I'm not. I have visited the facility and I've talked to their CEO. The company is now in Somerset, New Jersey. They had been in Lawrenceville, New Jersey. That's why it was Lawrenceville Plasma Physics. And they moved, so they changed their name. But as far as investing, you have to have enough in savings. But if you meet those requirements, you can invest with as little as $5,000. They'll take $5,000 initial investment. So if you want more information about that, see me afterwards. I'll be glad to steer you to whoever. Over here.
Are you guys looking at using any other waste energy off of it? There are a lot of heat that's pumping off of this. I mean, you essentially can make a TEG on the outside just for excess waste, and you can invert that and make it a TEC.
That's
to
right.
Cool down the area. So, I mean, if you're only using the electricity, you only get up to 99%. If you have the TEGs on the outside, you could crank it to 101% without too much problem.
That's right. I think this device could be used for a whole lot of different things if it works.
So that number is only, you said 9 nanoseconds or something.
Well,
Yes, the way it works, the plasmoid is formed, but it only lasts for 20 nanoseconds, which is an exceedingly short time. And then it disappears, but then you have another of these pulses of electricity. So you have 200 pulses of electricity a
It's
second.
pulsing. Like it's
Yeah.
always at 1.6 billion degrees every
Somewhere.
20
Right,
nanoseconds or
right,
whatever.
right. So most of
So
the
it's
time,
very
Close enough, that's close enough.
most of the time it's
Heat
not.
will diffuse out, and your entire device would heat up to a certain degree, you'd have to cool it.
Right, exactly,
I'm just saying, that's free energy.
Yeah.
right. I sat down with the CEO of the company and discussed everything with him rather carefully before I invested. I was quite impressed by what they're doing and what they've achieved so far. So
Yeah.
that's all I can say.
The materials are a big problem for tokamaks, because like their
Yes.
thing is that they have to be on for like ideally years at a time when they're only on.
Yeah, and on the tokamaks, they're planning to use deuterium and tritium fuel. Tritium is radioactive, and that reaction also creates neutrons. So your walls of the reactor become radioactive, and that means your facility can only last so long. And that's one of the reasons they think the tokamaks may not be economical. After they've spent $20 billion building one of these plants.
But you guys don't have the same.
Right.
Start over.
You guys don't have the same materials problems, even though
No,
you're a pulsed billion degrees.
There's no radioactivity at all, or no radioactive waste. You will have, while it's pulsing, you will have some X-ray radiation, but that's very, very short-lived. So, it's really not a problem.
So we just put it in the hospital.
Yeah, you may.
Want people buy it.
I think the only thing you'll have to replace regularly is the electrodes, because they probably will wear out with time. But just replacing the electrodes every month or so, that's not going to cost very much at all.
Yeah.
These electrodes are small; they're like that big. Yeah.
Just out of curiosity, on the triple product graph you have there, I know they haven't done any research in probably a decade or two. Was there any future for muon catalyzed fusion?
For which?
Was that muon catalyzed fusion? They did some research on it back in the 80s, I believe, and they hit a couple stone walls, and no one's really pursued it since.
Yeah, I'm not that familiar with that device, but I know there are dozens, perhaps hundreds of fusion devices, from the early days of fusion, and most of them have never been explored adequately.
Yeah.
So, one of these fusion devices is bound to work. It's just a matter of finding
Find the
them.
right ones.
Finding the right
Curious as
one.
to the credibility of it, because I have heard that there have been some ideas for creating a similar device that would create direct current
Right.
instead of relying on the age-old, heat steam turbine deal.
But token I wouldn't use that.
Yeah,
Yeah, I'm not a plasma physicist, by the way, so
okay.
but I am an aerospace engineer. I worked on the Apollo project a long time ago. I worked in aerospace for over 40 years.
Well, I'll
So-
find you afterwards, I have some other questions for you.
Yeah.
I'll ask everyone.
I'm not an expert in plasma, but I'm very enthused about this particular project. Yeah.
Just curious about the weight of this thing. How heavy is it?
I'll have it.
The mass of the device.
Well, I picked up the electrodes, and those are awfully light.
The whole machine, the 5 megawatt.
Well, I don't know. You can get an idea of looking at it. It's just a little taller than a person standing up,
But is it like a ton, 5 tons?
I would think maybe a ton
It
or
doesn't have any heavy metals in it, right? It doesn't have any lead or,
something.
so it's just steel and aluminum? Did you use aluminum
Well,
to collect the alpha rays?
um,
That sheeting is.
you have, your electrodes are enclosed in a vacuum chamber, but that's not that big. I mean, the
Right.
vacuum chamber is
So
rather
steel
small.
vacuum chamber and then wraps of.
Well,
aluminum foil?
there's that high-tech transformer device which actually surrounds the electrode, and that's all within the vacuum
What
chamber.
material is that, the transformer device?
I don't know.
If it's copper, it's still be pretty light, you just got steel, copper, and a vacuum
Yeah.
chamber.
I was just thinking,
Yeah.
because of a spacecraft.
Right, of course, like the Topaz weighs what,
Yeah,
4 tons, something like that?
yeah.
What kind of charged particles come off of the plasma filaments? I'm just kind of
Yes.
curious. Like, I mean, is it purely just electrons being discharged within the stream?
Well,
or-
it's actually, on one side, from the plasmoid, helium atoms get shot out in one direction, while electrons are shot out in the other direction.
So you get alpha particles and beta particles heading in opposite directions?
Yes,
Okay.
exactly, exactly.
You got positive and negative.
Right.
Let's say a cathode.
Yeah.
The cool thing is that you could use those, all of the x-rays that are coming off of it to actually tell you what your internal integrity is.
Yeah,
First quick
yeah,
process.
that's an idea.
But see,
Actually,
No, you just put, radioactive, or, plates all the way around it.
Yeah.
Just wait until it's done, for a couple hours.
yeah, actually, they've actually proposed this device because it can create a beam. They've actually proposed it to inspect bridges, because it's a way to cheaply find flaws in
you
bridges.
have a focused X-ray beam.
A focused X-ray beam, yeah, exactly, yeah.
With no residual radiation.
So, your proposed specific impulse of 1 million seconds, that's more or less based off of just the fuel efficiency of the reactor coupled with some sort of electric propulsion. So, it's not, I guess, while it's orders of magnitudes higher than what we currently have, the theoretical upper limit of direct fusion propulsion is 150 million, seconds. So, it's
Well-
still a decent shortfall from that. Is there a way to configure the reactor so that you can produce, an actual fusion reaction chamber to have direct fusion products?
Well, with this device, it's so small. They've actually calculated that it works better if the electrodes are small. That if they had bigger electrodes, it would be harder to obtain fusion. Because it's so small, you're limited in the amount of power that will actually be produced. So
You could chain up multiple reactors.
you can chain up multiple ones of these, that's right.
You could also feed the
Very
feed your
easily.
fuel in and have it open on one end, wouldn't you get a thrust? You get a high thrust if you pump your fuel in while your electrodes were going.
Yeah.
You'd
Yes.
you'd pump in
There-
boron and hydrogen.
Yeah, there are various
Thrust out.
ways to increase the thrust. One way is this thing produces a huge amount of heat, and you can,
Red hydrogen
that beam
passive.
will produce a lot of heat, and you can sort of have an afterburner type of
Oh, I
thing,
Is the-
where you use some other fuel that you heat up and it's expelled out of a nozzle. It would be almost like a nuclear thermal type.
Is the heat generated more or less confined to filaments? I mean,
Um,
what kind of
well-
shielding, what kind of shielding is there on the electrodes? I mean, from your diagrams, it didn't look like there's a whole lot of, really any much distance of shielding or magnetic
No.
shielding for that matter. So the heat must be confined to just the filaments, right?
Well, hopefully, yeah, the filament itself really doesn't fuse, so that the filament isn't
So it
the
lasts
problem.
about
It's
9
just that tiny
That
plasmoid,
interval with
that
time-
little ball.
The tiny interval, 9 nanoseconds.
Yeah, and that's, it's like, the plasmoid is only like a ball that's a few millimeters across, really small.
So each filament oscillates between the initial charge, the initial charge of electricity, and then it fuses, and then it just oscillates between those two
Yes,
iterate, okay.
right.
Well, it twists on itself, right? The
It
magnetic
twists.
field twists on itself just like a solar flare.
Right.
So that as the magnetic lines cross, that pinches off, and you've got an isolated spheroid of
Yeah,
current and.
you see these things in nature that's exactly right. It's a very complicated process that they don't fully understand, it's very hard to simulate.
There's like magnetic reconnections going on in the plasmoid?
Yeah.
Oh, okay.
You've got the current running through the ions, generating the magnetic field that holds the ions in place. So you get a self-perpetuating, just like a solar flare. Yes, exactly.
How do they measure that?
And reverse square wall.
I remember they talked about a bubble device that measures it. I don't know exactly how they do that, but they talked about a bubble device and some other measure. They've got two independent ways of measuring it, and they actually have obtained that temperature, which I think is amazing. I think most people thought that they wouldn't be able to do that.
If your X-rays are generated from the heat, then you could, from the frequency of the X-rays, you could backtrack to the temperature in the center of the plasmoid by looking at the frequency of the X-rays generated.
That may be one way that they're doing it.
Does anyone here like a physicist like?
I have a physics degree.
Oh,
Yeah. I'm not raising my hand.
I'm just curious. I'm a University of Maryland student. I'm a junior year, so I just.
I have a great deal of respect for the person who's the CEO of this company, Eric Lerner. He impresses me like he's a genius. He developed a lot of the theory, and LPP fusion isn't the only one working on this focused fusion device. There are a bunch of other companies working on it too, but he's developed the theory a lot more than the other companies. He's using smaller electrodes and a lot of other various changes and gotten far better results than the other companies working on this device.
Let me ask you a quick question. How do they protect their ideas? Okay, someone has a
Yes.
great idea for a fusion device. How do you go out there and try to promote it and get funding for it without someone saying, nifty idea? And next thing you
Well-
know, they're selling it
One thing, you have to file patents for one thing, to protect your intellectual property, which he's done. He's got patents that have been approved in several different countries, and you just have to you have to go out and find investors, and that's been a problem with LPP fusion. They've very much lacking in funds. They don't have any funds for spare parts or
I would say
anything.
given 500 million to 40 small companies rather than 20 billion
Yeah,
to design a device that actually it's not even designed to reach breakeven.
They need to do an
Right.
enterprise,
That's exactly
Right.
what we need to do.
the government-funded enterprise.
Absolutely, I mean, that's how we got spaceship
$1
one.
billion.
I agree with you. I
Some of the
think,
people funding it, are willing to take a chance because
Yeah.
they win the
If
enterprise.
talk to Bill Gates, tell him to offer $1 billion to whoever has a break-even fusion first. I guarantee you someone would do it.
Yeah.
If that was held up there, someone would.
Which actually kind of
I mean,
silly.
the most deals for the
You think that incentive would be needed considering if someone reached the break-even point, they would revolutionize every portion of the energy market.
Absolutely.
Yeah.
And
Because
it's,
the
it's just,
investors won't put money in unless they can see a known payoff. I mean, it is.
Well, but it's also that this thing has never, ever been shown to work. And so because of that, every single person that says, you know, oh, I could go out here and do that, well, go ask somebody to help you. Everyone's gonna say, you know what, I'm gonna go look for unicorns also. I mean,
Right.
that's what they say. I mean, I just dealt with a
Yeah.
quantum patent, and it's really tough to go through and try to convince people that, hey, your idea works when it says that it breaks every law of physics.
Yeah.
You know, the biggest law of physics says you cannot get more out of something than what you put into it.
Well, because at the quantum level, where you quantum foam.
Well, no, I'm just saying, like, you know, that's the problem here.
Yeah.
Is it says, hey, I'm gonna take something, I'm gonna shove 5 in, I'm gonna get 6 out. And everyone goes,
that's not
can't have it.
Yeah.
Because every other law of physics says no. I mean, it either has to be, you know, pre-stored energy. And so,
what is it, Stargate?
I'll start again.
Yeah.
What's the name of the fictional element that you just put energy in and it puts more energy in?
Unobtainium?
No, it wasn't called unobtainium in Stargate.
No, that was in the core.
I'm not forgetting what it's called.
But, I've always wondered how, you know, someone has a nifty idea and it just kind of dies. I mean, Tesla had tremendous ideas and he produced
Yeah.
so many incredible things, but he couldn't get the funding to actually produce most of them, and the ones that were produced immediately Westinghouse ran off with.
We'll never know, the Tunguska event was really.
That's right, he did it with that tower,
Right.
the White Cliff Tower.
Yeah, there,
I go for the meteorite.
Yes.
That's what it was.
With
Yeah.
today's environment, the patents are very difficult because all you do is you're exposing exactly what you're doing. And how many countries have you got covered? Yeah,
Well,
you got covered.
if you don't
I
apply
had some patents that were absolutely rock solid, and the Koreans came over winter work for my company. Stole all the technology, including the software that was really the hard part to develop. And went back to created a probe card that was so close to the one that we had, that the customer sent it to us for repair. It's the only reason we knew the company existed.
You
A
know,
company
the
called
Segway
Cyclone.
scooter that was copied so well by a Chinese company, the Chinese company made so much money, that when Segway sued, the Chinese company bought Segway.
Yeah.
Segway, and said, now we own the patent.